Hello everyone, welcome back to the second part of the mini course. The plan in this talk is to survey some pertinent results about instability and show how that leads into Theorem B. So let's get cracking. So the first relevant result for us is the theorem of Sao, Hamilton and Ilmanen, which proved that a wide class of Kähler-Einstein metrics are unstable. So maybe I should explain something about this. So whenever you have a Kähler manifold, you can study, look at the 1,1 Dobol cohomology group, which is, this notation means that. There's always a natural element in here, namely the Kähler form. The dimension of this cohomology group is given by this notation. H11 of M is the dimension of this group. So if it's at least 2, this means that you can find an element in here which is perpendicular to the Kähler form. That's the same thing as being trace-free. Furthermore, you can actually choose a harmonic representative, so then it's divergence-free. So now you should see how this is going to be related to the second variation formula, because you want something that is, divergence-free and satisfies the condition on the trace. So the next ingredient is, you see, if you have your tensor sigma lies in H11 of M, then, or your form is a 1,1 form, well, there's a natural way to turn a 1,1 form into a symmetric 2 tensor on a Kähler manifold, which is to put the complex structure into the first slot. So this gives you a symmetric 2 tensor, which has the right properties that you can use the formula for the second variation we saw in the last talk, because it'll lie in curvative 0. Then you directly compute with the Weizenbach formula, and you can show that the Legnerwitz Laplacian of this tensor is 0. And it's obvious then, if you go back and look at the formula, that this means that the metric is unstable, because then the only term left is twice the Einstein constant times the norm of this tensor. So that's how they do it. So we came into this subject, myself and Stuart, in 2011, when we generalized this results to the class of Kähler-Ricci solitons. Okay, so Kähler-Ricci solitons is the direct analog of this result, satisfying this dimension assumption are unstable. I guess the significance of this result was that there was a conjecture of Hamilton that non-trivial Ricci solitons, so Ricci solitons which are Einstein, are unstable, and every known closed example of a Ricci soliton at the time satisfies these constraints. So that gave some evidence to the conjecture, and in particular, it showed that stability is maybe a more interesting, or I guess subtle, question for Einstein manifolds rather than for Ricci solitons, non-trivial Ricci solitons. And that's maybe one reason why we're going to restrict to study this problem for Einstein metrics in this course. You can also view somehow Kähler manifolds satisfying this assumption. So if you take a product of Kähler manifolds, they'll satisfy this assumption. And so somehow you can argue that these results are sort of a generalization of the earlier result, that the product of two manifold, the product of 2 Einstein metrics is unstable. In general, maybe I'll indulge in a bit of shameless promotion here, but it's a difficult problem to show that a given Einstein manifold is unstable to construct. It's a difficult computational problem. So in the last talk, we were talking about how this is very easy to see for products. And maybe the most natural generalization is to look at work product metrics. And we recently showed that in low dimensions, all work product Einstein manifolds are unstable. But even here, like, this was a computationally challenging. So we really don't know. And this is going to be something you will see later in the talk as well, as we talk about the situation with symmetric spaces. There's an interesting question in this paper, which is really the genesis for a lot of what I'm going to talk about today. And it's where we start to see a connection between the spectral geometry, so of say the ordinary Laplacian on our manifold, and stability under Ricci flow. So they have a question in their paper. Suppose we take an ordinary eigenfunction of the Laplacian, let's call it U, and suppose that it's, let's look at the largest possible eigenvalue, the first eigenvalue. So the question that they were interested in is, they said, can you find an example of an Einstein metric? Remember, I'm always dealing with closed Einstein manifolds, so the Einstein constant is positive, such that the first eigenvalue is bounded below by minus 2 lambda. So for some motivation for this, there's a well-known theorem of Matsushima. When you have a Kähler-Einstein metric, there's always an isomorphism between the space of killing vector fields and this eigenspace of the Laplacian. And so in particular, minus twice the Einstein constant is realized as an eigenvalue once you have isometries, say for CPN with the Fubini study metric. But they were interested where the first eigenvalue could actually be slightly larger, and there was no known example. Now, why were they interested in this? Well, this construction is going to come up later in the talk as well. So if you take a function, say, with mean value 0, there's a natural way to cook up a symmetric 2 tensor. So let's call this S of u, this map, S for symmetric, I guess. So you take this multiple of the metric and subtract off the Hessian of u, and a direct computation shows this lies in the space kerr div 0. So that's very good for us because that's going to be very useful when we plug it into the formula for the second variation, which the simplified formula. Another nice feature is that this operator, or this map S, kind of plays nice with respect to the natural Laplacians which are floating around. So if you start with a function u and construct S of u, that's a symmetric 2 tensor, and you can compute its Licknervitz Laplacian. And that's the same thing as taking the Laplacian of u, which is a function, and feeding that into S. Okay. So why this is important is if you have how this connects back to their question above about eigenfunctions of the Laplacian, is that suppose you have an eigenfunction of the Laplacian, and for this eigenfunction u, you look at the tensor S of u. Well, S of u, let's take its Licknervitz Laplacian. By this formula above, that's going to be S of the Laplacian, but this is an eigenfunction, so this is lambda u, and lambda pulls out. And as an upshot, we see that S of u is actually an eigenfunction, an eigentensor of the Licknervitz Laplacian with the same eigenvalue. If we feed this into our formula for the second variation, what do we get? Well, the 2's and the half cancels, so let's see what we get. So the second term here we take our second variation. This lies in the right space to use our simplified formula. So we plug it in, and see the second slot here, you have the integral of S of u with itself. So this is the norm of S of u squared times twice times the Einstein constant. So that's this term. The first term is going to be the Licknervitz Laplacian times S into S of u. By what we've seen, that's S of the Laplacian of u. And if this is an eigenfunction with eigenvalue lambda, you pull out the lambda and you just get the norm of S of u again. So what you end up getting is lambda plus twice the Einstein constant times, this is a positive quantity, and a positive quantity. So now you can see why they were interested in their question. If you could find an eigenfunction such that this number lambda, the first eigenvalue, say, was bigger than minus twice the Einstein constant, this quantity would be positive, and you would have proved that the second variation is positive. It's unstable under Ricci flow. So, but there was no known examples, and so this was an observation they made in their paper. And this is going to be relevant because even in low dimensions, so here's a table of what we know in low dimensions, and it's still not complete in dimension 4, for example. So how this is relevant is, I'll explain now. So here are, say, let's just say 4 manifolds, Sn, you can do this in higher dimensions. The round metric is always linearly stable, so we understand what happens there. The Fubini study metric, this turns out to be neutrally linearly stable because this is the first eigenfunction of the Laplacian is given by this value, by Matsushima's theorem. I'll come back to that in a sec. CP1 cross CP1, or S2 cross S2, is a product, so that's trivially unstable. These guys down here, the Einstein metrics are due to Hsu and Tian. Well, they have H11 bigger than 1, so they're trivially unstable. And then we have these other 2 metrics. And a few years ago, together with Hall, we actually answered this question of Cao, Hamilton, and Ilmanen and showed that the first eigenvalue satisfies this bound, which in particular implies that it's linearly at the page metric, which is the first example of an Einstein manifold, which is not a symmetric space, can be destabilized by this method. Okay. How did we prove that? Well, the page metric is very special. It's conformal to an extremal toric Kähler metric. And so that's a lot of very rich structure that you can play with because you're interested in studying the Laplacian, but you know how the Laplacian transforms when you under conformal changes of metric. And so you translate this question about the Laplacian into a question about the Laplacian of the toric Kähler metric, and we explicitly compute the Rayleigh quotient in this framework. Okay, and we managed to prove this result. So this proves that the page metric is unstable. I should say here, it's still an open problem. There's an analogous metric to the page metric on CP2 blown up at 2 points, which is called the Chen-Lebrun-Weber metric. This is also Hermitian, but it's conformal to a extremal Kähler metric, which is toric, so it's a very similar framework. But even here, this is actually an open problem, and definitely would be great to know the answer to this if you're interested. So we do not know anything about the stability of the Chen-Lebrun-Weber metric. Now, a very important contribution to the study of stability was made by Cao and He in 2013, who investigated symmetric spaces and sort of made an exhaustive list of what we could say about their linear stability. So here's the list. We're interested in the neutrally stable case, where H11 is 1. We're interested in the neutrally stable case. Here's all the examples which are neutrally stable in their list. G2, for example, isn't a Hermitian symmetric space. But the first 5 spaces on this list are. They all satisfy this assumption, this constraint, because otherwise we would know they're linearly unstable by the argument I just outlined before. And so we don't know what happens with the stability of these guys. Now, I would say the subject somehow got a shot in the arm or a great boost with this theorem of Klaus Krünke from 2013, who proved a really surprising result. There's a very nice exposition of the ideas of his work given by Knopf and Seesum in 2017, who also worked out their own proof of this. So suppose we have, so the situation is the following. Suppose we are neutrally linearly stable. That means the second variation vanishes. So suppose we have, this means we have a function on our Einstein manifold, which whose Laplacian lies in the minus twice the Einstein constant eigenspace. So then this will be this perturbation will be neutrally linearly stable, and it's natural to look at the third perturbation, and he got this very nice formula. So the third perturbation is given by this multiple, m is the real dimension of the manifold, times the integral of the eigenfunction cubed. So this is very nice because, well, for third variations, it's enough to show that if you have a neutrally linearly stable perturbation, it's enough then to show that so the first variation vanishes, the second variation vanishes, then it's enough to show the third one is non-zero, because because 3 is odd, so you can multiply your function by -1 if you need to give it the right sign. And so somehow you can prove that a neutrally linearly stable manifold is unstable, is unstable under Ricci flow by just computing this integral and showing it's non-zero. And so now you see the connection with earlier, hopefully, that this is connected with like natural questions in spectral about eigenfunctions of the Laplacian. So he used this to prove the following result, which is the real take-home message, namely that the Fubini study metric is unstable. And this was definitely a surprising result because there was a conjecture of Hamilton that the CP2 is stable. So how does he do this? Well, it's a corollary of his theorem. So he explicitly writes down eigenfunctions of the Fubini study metric. He does this via the Hopf vibration, so he pulls them back up to the sphere, where you can compute with spherical harmonics, and he shows that the integral of the eigenfunction cubed is non-zero, and so therefore you can destabilize via this formula. So theorem B is a generalization of this. Of course, we don't have the Hopf vibration in general, so we have to try something new. So the statement is that when n is not equal to 2k, the complex Grassmannian of k-planes is linearly unstable, dynamically unstable. So that's the theorem. When k is 1, you get back to CPNs, and that's Krünke's result, we notice that when k is 1, you can't have n being 2, because that would be the 2 sphere. That's not allowed. So that's okay. Now, how do we prove this theorem? Well, we use exactly the idea from Kronke's proof. We explicitly find eigenfunctions of the Laplacian who which lie in the minus 2 times the Einstein constant in that eigenspace, and we show their cube. When you integrate the cube, you get a non-zero quantity. So same strategy. Of course, probably the natural question is, you might say, well, why don't you try this for the other symmetric spaces? And so for the other compact irreducible Hermitian symmetric spaces, we actually prove that this approach can never work, because whenever you take, which is a sort of a cute result, I guess, independently, whenever you take an eigenfunction of the Laplacian in this eigenspace, if you cube it and integrate it over the manifold, you must get 0. So this approach, the third variation, will always vanish for the other symmetric spaces, and these are the only ones we can say something for. Now, I should say a little bit about how the proof of this goes. We use the framework of describing the Hermitian symmetric spaces via coadjoint orbits. This is all very well outlined in say, Besch's textbook. But somehow what happens is you choose an element of your Lie algebraic psi, and then via the, say, action of the adjoint group, you can, if you look at the orbit of this element under this action, you can realize this as this orbit you can realize as the Hermitian symmetric space. And it's a very nice framework, because all of the geometry is sort of encoded at Lie algebra level. So if we take an ad-invariant inner product, say the killing form or something, one other thing we're going to need is that the Lie algebra G is going to be isomorphic to the space of killing fields. That's a standard fact. And so, for example, just to show you how everything can be encoded at this level, the Kähler form, so this is symplectic form, this is it encoded at Lie algebra level. So if you're looking at the orbit which is generated by Xi, this gives you the Kähler form. This will of course be the Kähler form for the Hermitian symmetric space metric. Okay, so we're going to work in this framework, and we need to write down eigenfunctions of the Laplacian. We need to show that their eigenvalue is minus twice the Einstein constant. And then we need to worry about cubing these guys and integrating them over the manifold. That's the mission. Okay, we can show that that's not 0, then that's how we show that things are unstable. The functions we take actually are these functions, which are already well studied in the literature. They actually appear in the work of Bott, which I'll mention at the end. So if you take an element of the Lie algebra eta, you can identify that with a killing field, and then you can sort of take, this is the function evaluated at the point z, where z is a point in the orbit, so a point in your manifold. You can view this as an element of G, and you can take this inner product with respect to our ad-invariant inner product, and that gives you a function on your manifold. And so just to give you an idea of how these proofs work, this is going to be an eigenfunction in the right eigenspace, and this is going to be these are going to be the eigenfunctions we study. So maybe I'll say something like this. This is a homogeneous linear polynomial, and it lies in the right eigenspace. So then we can look at the cube of this guy and integrate it. So it's a homogeneous linear, it's a polynomial if you write out the Lie algebra in local coordinates, is what I mean. So for example, how do you see it's linear? Well, that's easy to see from the formula, right? If you scale z, if you scale it by a constant, you can see it just immediately follows from some linear algebra. How do you see it's a linear polynomial? Again, it just comes from this form, right? If you just write out what's an inner product in linear algebra, you can see that this is going to be a linear polynomial. Okay? And so the maybe interesting thing to talk about is, how do we show that this is an eigenfunction of the Laplacian on this manifold, the right eigenvalue? So we have this decomposition that I talked about in the first talk of symmetric spaces. So we choose x. Let's do this computation, say, at the origin. And you consider the function of t, which is given by, you look at the image under the adjoint action of psi under the x of tx, and you evaluate your function at this point. So by definition, that's given by this. And because you have ad invariance, you can bring the ad over to the other side, and you get this quantity. Okay. and then you differentiate. And now you should see where I'm going with this. When you differentiate this, you see when you differentiate the adjoint map, you get this map, you get the ad map here. And this is exactly the symplectic form, as I explained on the last slide. So it's minus the symplectic form, but the symplectic form on a Kähler manifold is given by taking the Kähler metric and putting j into the second slot. And so the derivative of this function is given by sort of the inner product, or evaluating the metric by putting x in the first slot and j eat in the second slot. However, this is how you would usually talk about the gradient of a function, right? So this is telling us that the gradient of our function phi is given by this quantity j eta, where eta is a Killing field. And that's really it, because Matsushima's theorem gives you an explicit isomorphism between this eigenspace and j times the space of Killing vector fields. This is the isomorphism. Okay, so if you have any eigenfunction of the Laplacian that's isomorphic to j times the space of Killing, this is a Killing field, so this is j times a Killing field. And so this means that this function must be the gradient of this function, must be realized as an eigenfunction of the Laplacian with this eigenvalue. Okay, so there's some details skipped here because now you have to do this over the whole manifold, but this is the basic idea. Okay, so it's a homogeneous linear polynomial in the coordinates. Well, what do we need to do with this function? It lies in the right eigenspace. We need to cube it. But when you cube it, because it's linear sort of from this explicit form of it, so when you cube it, you get something that's a cubic polynomial. So the stability integral, f should be phi here, phi eta cubed is going to be a multiple of a homogeneous degree 3 polynomial in the basis elements of G. Now, we can sort of apply some machinery from representation theory, because we can basically restrict this to using the Chevalley restriction theorem. And there's a theorem called the Chevalley-Shephard-Todd Theorem, which explicitly states the generators for the graded algebra of invariant polynomial functions on a Lie algebra. And the point is this is going to be a cubic G invariant polynomial function on the Lie algebra. G is the group. So we now know that the obstruction, or what we want to compute, is going to somehow be a multiple of this generator. Okay, so then the question is, well, where do we get generators? And if you look at the Chevalley-Shephard-Todd theorem, so here's the root systems of the simple Lie algebras, and here's the degrees of all the generators. And we must have a cubic. So there's only a 3 in one place here. And so for all the other Hermitian symmetric spaces, there's a Hermitian symmetric space corresponding to each of these simple Lie groups. You're going to get, you have no generator of degree 3. And so that means that the only possibility for a homogeneous degree 3 polynomial is a trivial one. So this is how we show that the integral of the eigenfunctions cubed is 0 for the other guys. So that's the bad news. That's why this approach won't work for the other eigenfunctions, for the other Hermitian symmetric spaces. But there's still a case when the Lie group is SUN plus 1 that we have to do some computations. So we have to compute the stability integral when our group is SUN plus 1. And now, of course, this is a direct computation with one specific Lie group, which is very nice and well understood. But it's still a non-trivial problem, because we have to compute the integral of this eigenfunction cubed, not just the eigenfunction. So how are we going to compute the integral of the eigenfunction? So to do this, let's let T be a maximal torus, and there's a corresponding Weil group which is realized as the normalizer of this torus mod T. Choosing eta carefully, there's some constraints to lie in the maximal torus. You're going to get a circle action. When you have a circle action, there's a very nice formula called the Dustermaat-Heckman integral formula, which is going to tell you, this is the statement of the formula, but somehow it relates the integral of this function to the sum over the critical points of this function evaluate this sort of weighted sum of the function at critical points. And the weights here come from root space decompositions and all have to be calculated. So what we can do with this, which is, I guess, a trick which other people have used, is to differentiate this with, this is a function of t. So now we're going to differentiate it 3 times and set t equal to 0. So this is an elementary piece of calculus. When you differentiate this and set t equal to 0, so we'll see each time you differentiate it, there's no t here. So the only place there's a t, it's e to the minus t times your function. So each time your function comes down. And then if you differentiate it 3 times and evaluate it when t is 0, then this quantity is 1. You just get the integral of phi cubed up to sign. Okay. So going back, this is going to give us the integral of phi cubed. This is something that we can compute in terms of root space data. We have to differentiate it 3 times and compute it in terms of root space data. That's where the computation gets involved. So the right-hand side and its derivatives can be computed in terms of data attached to the Lie group. And the main idea is that this lemma of Bott. So for this function, this is how we started studying this function. The critical points exactly arise as the orbit of eta under the Weil group. And so you know what the Weil group is, you can explicitly compute all the critical points, and so you can explicitly compute at the right-hand side, and so you can explicitly compute this and show for the right choice of eta that this integral will not be 0. Okay, so that's effectively the key idea for the proof of theorem B. And that's the end of the second talk. So in the third talk, we're going to explore connections between this and the rigidity question for Einstein metrics. All right, thanks.